So now that we've seen essentially very different kind of behavior just between the Q4 and Q8 element for the full and reduced integration, we need to ask ourselves, why is the Q4 reduced integration element, why does it behave so much differently? Okay, and in order to answer that, we really have to look a little bit more deeper, investigate a little bit more closely what's going on. So the one thing that we've learned from 1D was we could always go and look at sort of the deformation modes and strain energy associated with those deformation modes. So this is what I want to do now. I want to say, let's look at this Q4 reduced integration elements, strain energy deformation mode. Before we do that, let's just make sure we're comfortable with what we know we want to expect. So first, let's do the full integration Q4 element. And for that, I've created a sort of fair main program modified. And the only difference with this modified program is the following. Where did I store it? One of these. Is I'm returning the typical element and the coordinates for the atypical element in that mesh. And so all I'm doing is when I go through this sort of loop of the elements, I just make a copy of k element and the x and y coordinates for the element. And this is what I return. Now, this is really the only modification between this and the normal fair main program. Okay, so it's a really small modification, but it's an important one. Okay, so this is what I would like to say is first off, when we think about a Q4 element, okay, so this is now a Q4 element, we need to ask ourselves, what is the dimensions of that, what is the size of that stiffness matrix first. So Q4 element has got 2 degrees of freedom per node, so 2 unknowns per node, and there are 4 nodes. So we expect to see an 8 by 8 stiffness matrix, yeah, because the 4 times the 2 is 8, so that's the total number of degrees of freedom, so that stiffness matrix will represent an 8 by 8 matrix. And so there should be 8 eigenvectors and 8 eigenvalues associated with that. That is just one sort of. And if I think about just the unconstrained element, there must be some rigid body modes associated. I'm doing a fully integrated element, and the rigid body modes that I expect to see in the 2D planar case is essentially translation in X, translation in Y, and some rotation. So I expect to see, and again, the rotation is very small angular rotation, but I expect to see 3 rigid body modes, because that's the kind of, in terms of small rotations, I would still like to see the fact that there's no energy associated for very small angular rotations. And we saw what happened when you have large angular rotations. There's lots of strain associated with that because of the linearization that we've done. But this is, first off, just to sanity check before we start looking at representation. Let me just see that. So I expect to see 3 0 eigenvalues, and the modes associated with those 3 0 eigenvalues to look like stuff that looks like, essentially look like rigid body motions. Okay, so to do that, all I'm going to do is I'm going to run this Q for 2x4 pool 1. This is exactly the same thing what we looked at now, the same input file, fully integrated. And let's run it. So make sure that we load this k element x, y. And all I'm doing here is essentially I've just written a small piece of code that just takes this k element, computes the eigenvalues and eigenvectors, and then essentially all I'm doing is I'm plotting. I'm really just plotting the eigenvectors as nodal displacements. So I can choose here the mode that I want to look at for the eigenvector. So mode 0, 1, 0 to 7 for the 8 modes that I have. Okay, so that's really what I have available here. So let's run through this and see. Okay, so first off, yeah, so that is really, I can just to give you an idea, this I counter that I've got here is just for me to go through the loop through the nodal points. So it's for every point in x, y, I just use this to loop through that. The nodal, so I can do the nodal displacement for each of those points. Okay, when you see a black dot, that is the undeformed, and the red dot will be the deformed point. And all I'm doing is I have a scale factor here, so I can just scale the eigenvectors. So I can make it smaller or larger, the scale factor associated with that eigenvector displacement, just for visualization purposes. So let's start off with mode 0. First, let's run through these modes and make sure that makes sense to us. So if I look at this mode, I can see here my black dots are this. This is essentially my element. Now all of them have moved out like this, so uniform expansion. And when I look at that eigenvalue associated with that, we see a value here in the mode in the range of 300,000. Okay, so let me just open up here a a place where I can just write. So I'm going to say mode 0. So I see here the value for the eigenvalue is associated with 30,000, yeah? 1800,000, and then I can say when you interpret it is it's uniform expansion. Okay. So that's really just to make sure that we can keep track of that. If I look then at, say, let's do the next mode, and I'm still going to formally go through this in another notebook where we go through this eigenvectors. I just want to first just run through logically what's going on here. So when I look at this one, I need to ask myself what's going on here. So this looks to me like sort of a mixture between a small translation in X and a small rotation, if I have to look at that. So if I look at the black dots, all of the black dots have moved a little bit to the left, so there's a small translation aspect there. And it looks like if I look at this point, it's going down, this point's going up, this point is going down, this point's going up, small rotation associated as well. So I would say mode 1, it's got a 0 eigenvalue associated with it. This is numerically 0. And then I can say, well, this looks like a translation in X plus a small rotation. Okay, just take you through this logic. If I look at this point here, all of the points, the black dots, have moved to the left. So that's the translation in X. And a dot here has gone up, the black dot here has gone up. On this side, the black dot has gone down, and the black dot has gone down towards this red dot. So a rotation would do exactly that. A small rotation would make on the one side the points go down, on the other side make the points go up. Okay, so that's that. Then I can say that's fantastic. Let's look at mode 2. What is mode 2 looking like? Mode 2, it's got an eigenvalue of 161,000. And what does this look like? If you look at this, this looks to me like shear behavior. So this almost looks like this thing is pulling like this, pulling like this, pulling like this, pulling like this. So it's almost like a shear kind of behavior if I look at that. So mode 1, 2, it's got 161,000 thereabouts, and it looks like shear. Okay. Mode 3. Mode 3 looks to me like at the top it's expanding, at the bottom it's contracting. So it almost looks like a crude version, if I can put it like this, for bending, where at the top it's in tension, things are going out, at the bottom it's in compression. So imagine I'm taking a beam, a rectangle, and I'm putting a moment on it such that the top is in tension and the bottom is in compression. This is what one might expect to see. Obviously, we would like to expect to see some curved stuff, but we only have 4 nodes. So this is sort of looks like a bending kind of phenomenon. So mode 3, you can say it's 103,000. So let's call it just 100,000. Right, that's what it looks like bending. Okay, mode 4. If I look at this carefully, I can see this again looks to me like shear. Yeah. So this looks again like shear, but in the sort of in the opposite direction to what we had previously. So mode 4 looks to me like shear. It's again 160,000. Mode 5. I'm going to look at this. This looks again like bending to me. So, bending. This pulls out to the top, so here's tension, and this side here you can imagine there's some compression happening. So that's sort of a bending where you apply the moments sort of on this side. So a moment here and a moment here, squeezing this and pulling here. So that's mode 5, looks like a bending mode. And if I look so far, I've only seen essentially one 0 strain energy modes. I expect to see more. So my gut feeling would now be that the next 2 should be 0 strain energy modes, mode 6 and 7. So let's look. So mode 6, you can see it's 0. And when I look at this, we can see there's again some slight rotation going on here. So this looks to me like a rotational kind of mode. Rotation with some slight translations in there. Okay. So that's, if I look at that, all of these points have moved essentially down, and then there's some slight rotation going on, where these points have moved lots in X, and these points have moved a little bit. It's almost like rotation around the other axis. So I would say some translation in Y and some small rotation. So that is for mode 6. And then if I look at mode 7, this looks to me largely like a translation in Y. Okay, so that looks very close to just a translation in Y. Okay, also zero strain energy associated with that. Translation in Y, that's, if I look at that quickly, that looks more or less like that. Maybe in a slight rotation, plus again a small rotation. It's not 100. And the reason is all of these points have moved down, but I can see here essentially these points have moved slightly up again, and these ones have maybe still slightly more down because of that slight rotation that's happening. Okay, that's essentially what we have. This is now for my fully integrated element. So now that we know what to expect for a normal fully integrated element, so this is the FI element, fully integrated. Let's look at what happens with a reduced integration element. Okay, I maybe just want to do it like this so we can see it nicely. So I think a bit more visible. Okay. So now we can see that. Let's change this element now from full integration to reduced integration. So now we want to see what changes by just changing the integration type from full to reduced. So this is again these crazy kind of displacements. Look at that start back. And now let's understand what's going on. Let's start with mode 0. And see what we learn here. Okay, so if I look at this eigenvalue, it's again 300,000 uniform expansion. It looks exactly the same as the mode that we had for the full integration. Nothing has changed there. Can you see that? Nothing has changed there. If I go and I say, let's make it mode 1. Mode 1 looks, if you look at this, what's going on here? It looks to me like some rotation with some small bending. The reason I say that is this node is almost the same as it was. This one has moved in, this one has moved out, and this one has moved out. So it looks to me like bending plus a small rotation. It's not just translation in X because things are. So this looks to me like, to be honest with you, mode 1 looks to me like bending plus small rotation. Okay. If I say mode 2, what's happening here? Another zero order mode. This looks to me, so let's look at what's going on here. This looks to me like a possible, so this point is going up, this point is going down, this point is very similarly, and this one's going up. So this again looks like a bending rotation kind of thing. If I have to give some view on that. Okay. This is going up, this is going down, so that's sort of that side is sort of in tension. This is going up a lot, this is going up very slightly. So we can think of this as being more or less in compression, that edge, and then essentially I think there's some, the fact that this is going to the left and this is to the right, indicating some rotation that's happening there. Okay, so let's look at mode 3. This looks to me like the standard kind of shear that we had before. Look at that. So it looks like pulling the thing like a shear, where it gets pulled like this and gets pulled like this. So that looks like that kind of shear mode. So I'd say mode 3 is a shear mode. And the energy is again 160,000, so nothing has really changed there. I think just put these as 1 because it's also the same values really. So that's that. Mode 4. If I look at this, again it looks to me like shear like this. So it's like, again, it's a shear mode. You can see that sort of, that edge, that sort of shear when it gets pulled like this. Poof. That is nice. Mode 4 is got shear. Mode 5. If I look at this mode 5, this at the bottom looks again like it's pulling out. It's tension, compression. It's again some bending with some some bending with some slight translation, rotation. Mode 6. It's again a zero energy mode. So what is happening here? This looks like a small rotation. Small rotation with some maybe translation next. And then lastly, look at this, again a zero energy mode. And again it looks to me like some rotation slash translation. If I look at this, it looks to me like something in that regard. Rotation, translation kind of mode. Translation. So maybe translation in Y. Oh, so in X, yeah. That's X is fine because these points have moved to right, and then some more rotation associated. It's something in that regard that we see. Okay? So the important thing is things have changed. And the important thing that I want to show you what has changed is the following. Is, if we look now carefully what's going on, okay, let's just highlight first what is the same. The uniform expansion, exactly the same. The shear, exactly the same. It happens for different modes, though, but that's not so important. The shears are exactly the same. What's happened is all our bending modes have become blended with, essentially become zero energy modes. So every time when you see the word bending, it was essentially associated with exactly zero strain energy. Can you see that? With zero strain. So now, so that's really what has changed. So the things have stayed the same. Shear stayed the same, uniform expansion stayed the same. But our two bending modes that was here, that had lots of strain energy associated with it, has now zero strain energy associated with it. And so the implication is, our reduced integration element has 1, 2, 3, 4, 5 zero energy modes. And so you can imagine, if I take an element and I put it into bending, and I say there's no energy associated with it, no strain energy associated with it, that is quite crazy. And what's happening is, the communicable mode is, that can propagate through the mesh. And that's what's causing the havoc that we're seeing. Is essentially, when I have that bending, let me see if I can sort of put down the bending here. If I put it down like this. And we'll still go into why this happens. For now, it's important that you understand that it does happen. Okay, so if I draw that sort of crudely. So if I say the element can let's do this like this. If the element deforms in this way, for instance, what we are saying is, with this reduced integration, there's no energy associated with that deformation. Okay, no strain energy associated with that kind of thing. It's compressing at the top, tension at the bottom. That is a big thing, and that's what the communicable mode is. And the reality is, I can have two of them on top of each other. I'm going to show you. If I do it like this, I'm just going to swap this long one and the short one. And say instead of looking this way, it's maybe looking this way here. So there's now another element here at the top that's also bending. You see that? Bending. My ASCII art is not bad. Bending. So if I have an element here that is sort of in a bending kind of mode, and I've got an element here that is in a bending kind of mode, and they're on top of each other, they're like, what does this look? It looks like an hourglass. And so if I have lots of these elements like this next to each other, again, where there's here, there's maybe, I'm going to show you this, where this is here, another element that I'm putting down now with my ASCII art kind of version. Can you see what I'm doing here? I'm stacking these elements quite easily next to each other. Yeah? And this pattern that I'm forming here fits beautifully to each other. No problems. Can you see that? And let me just get this short running. What I'm trying to tell you is, the beauty of this is, I can deform a Q4 element, this 4 elements into this shape. When I have reduced integration, there is no strain energy associated with this kind of deformation. And I know that doesn't make sense, because when I take that mid-side node and move it around like this, you'd expect to see lots of strain energy associated. If you have a piece of steel pattern and you're trying to move points in that steel so that things in the form shape look like this, there will be lots of energy associated with that. But the reduced integration sees no energy associated with that. And that is the issue that we have. So this is not going to work. Okay, so that's, to see it, please double click on this ASCII art. But this is the issue. And that's why almost all modern file packages has what's called hourglass control. And this is to try and prevent this kind of modes from propagating through the mesh. And it's the same thing that you can often switch on and off, but you have to realize that sometimes just clicking here or there can have large consequences. And the reality is, this is all obvious. This is all good and obvious in this kind of scenario here. Look at this. This is all good and obvious here, because look, the thing looks like a star. It looks nonsensical, but I promise you, if you have a complex mesh, and there's a communicable mode in only a part of that mesh, you can have some interesting stresses that are forming there, and the displacements are not going to necessarily explode like a star, like crazily like this. It might look just a little bit more conspicuous, and I want to show you this point in the next video. So I'm going to run out of time, so I'm going to show you in the next